This is ECE E343, Signals and Systems. This will be the fourth part to Chapter 4. In this lecture, we're going to take a look at transform domain analysis of circuits. What we'd like to do is we'd like to be able to just take the Laplace transform, not of just a differential equation, but of an actual circuit. So draw out the circuit representation and transform that pictorial representation of the circuit to convert it from a time domain representation to a frequency domain or a transform domain representation, which will facilitate the solution of that circuit. To begin this, what we'll do is we'll take a look at a couple of transform circuit models for components like a capacitor and an inductor, and then we'll go ahead and demonstrate the technique through an example. So let's begin by taking a look at the idea of a capacitor. We've all had circuits before, so we know that if we apply a voltage, right, and we let that run through a capacitor, right, we have a basic simple electric circuit. And we can take a look at this guy and think about there being a induced current going through there. So we could have a current I of t that's flowing through that. We have the voltage x of t applied to that capacitor. And we'll go ahead and let the capacitor be of capacitance C. And we'll assume that it has some initial condition, that there is some VC at 0, right? So we have some particular capacitor voltage on there as well. If we go ahead and we take that circuit and we Laplace transform it, and because I've drawn this with an initial condition, we know that the unilateral Laplace transform is the appropriate one. We're going to basically transform every element on that circuit picture, right? And we're going to come up with a transform domain equivalent. I'm going to go ahead and draw it out, and then we will verify that indeed this thing is in the correct representation. So I'm going to go ahead and write over here the transform of the input. We're going to call that x of s, something along those lines. And then it's going to feed into that capacitor, so no problems there. So we're going to have our capacitor in there. The transform of the current, we're just going to let the I of S. And then we can take a look at that capacitor. And what we're going to do is we're going to represent it with its impedance. And in the transform domain, that should be 1 over CS, hopefully something you've seen before in circuits. The thing that's kind of interesting in this particular case is what we do with the initial condition. And that initial condition is going to come up and show up as a voltage source in series with that capacitor. There's also a parallel way of dealing with initial conditions. Those are in the book and one that I'm going to have you derive for one of the homeworks coming up. So in this particular case, we're going to just do it as a voltage in series with the capacitor itself, and it shows up as a VC at 0, right, over S, something like that. And then we're going to go ahead and close that guy out, and we had our original input voltage, right, x of s. It's still the same thing. So we're talking the voltage across that capacitor in series with that initial condition generator, if you want to talk about it that way. So this is the transform domain equivalent to this capacitor circuit. And what I'd like to do is I'd like to go ahead and prove that this is indeed the equivalent circuit model in the transform domain. What I'm going to do is I'm going to go ahead and take the ideal voltage current relationship for a capacitor. And so I know that for a capacitor, the current I of t is equal to the capacitance, right, times the time derivative of the voltage on that capacitor, which we took as being x of t, something along those lines. And I'm going to apply the unilateral Laplace transform to that differential equation. So there is an underlying differential equation to this. If I do that, I know that the transform of a signal, I of t in this case, is just going to become I of s, no problem in there. Go to the other side, Laplace transform is a linear operator, so the c can be pulled outside. And then I'm taking the unilateral Laplace transform of a first order derivative. We know what that looks like. The derivative itself is going to give me an s, x of s, something like that. But then there's that initial condition. That's the kind of special property of derivatives with the unilateral transform. So I get that minus VC at 0, something like that. Now, if I just write this in terms of what is the voltage, x of s, I can rewrite this whole equation. So I'm going to just simplify. We will simplify and solve this guy for x of s. Okay, and if we do that, we end up getting pretty straightforward in this case. X of s is being equal to, well, I'd have to divide both sides of the equation by c. So I would have 1 over c I of s, right? And so I would have, in this particular case, a 1 over c, and I had my I of s. And then the initial condition, which was represented as a minus VC at 0, would be brought to the other side. So that would be a plus VC of 0. So I would get here a plus VC at 0. But then I had an s times x of s, so I'm going to have to divide by that s. So I'm going to get a divide by s on all of these guys as well. So that's just rewriting that equation that we got directly from taking the unilateral Laplace transform of the ideal voltage-current relationship for a capacitor and showing it in terms of that applied, or the voltage across that capacitor, the x of s, if you will. If we go back and look at this then, right, what do we have? We can think about this as a loop. There is the overall voltage in here, right? We have x of s, and if we go around a loop, we know that that voltage x of s has to be the sum of the voltages across the loop. And so what do we have? We have a current I of s, right, going through an impedance 1 over Cs. So the voltage on that, according to the transform domain version of Ohm's law, right, if we think about, just as a little aside, we know Ohm's law looks something like V equals IR in the transform domain, where we can allow for more generalized components. It is what? The voltage equals the current times the impedance Z, something like that. So that's the transform domain version of Ohm's law. So the voltage that's going to be going across that capacitor, right, is going to be the impedance 1 over Cs times the current Is. That's this term right here. And then I have the second voltage in there, which is shown just directly as a voltage source, right? And that voltage source is VC0 over S, which is exactly what we had written over here. So very easy to show that this simple circuit that I've drawn, where I've transformed a time domain circuit and put it into the transform domain, right, that capacitor gets replaced with a capacitor in series with a voltage source that is dependent on that initial condition. We're going to do the same sort of thing so that we can get an equivalent circuit in the transform domain for an inductor. So let's go ahead and take a look at that as well. I'm going to go ahead and have an input voltage x of t, and I'm going to let it feed in again into a circuit that's just purely this inductor, something like this. And we know that there can be a current going through there, so we'll call that guy I of t, and we'll let the inductor have an inductance L, something along those lines. This could, again, also have some initial conditions. We usually think of initial conditions for an inductor in terms of its current. So I'm going to think of I sub L0, right, being the initial condition on that inductor, some overall current going through that inductor at time t equaling 0. If I go ahead and unilateral transform this, and again, I do a unilateral transform because, right, there's an initial condition saved here, I end up getting that x of s, no surprise there, and it's going to come over here, and I'm going to have that inductor again, but it's the transform of that inductor, so we're going to get the impedance of that guy, which happens to be L times s. We still have a current going through that path. That's going to be I of s, and then we're going to end up having, again, another voltage in series. There are parallel forms, like I said. You can see those in the book. I won't cover them in lecture. And this one's going to have an opposite polarity, so it's going to be a minus plus, and it's going to be L times I sub L at 0, that initial condition. So again, this thing depends on that initial condition that was given. Okay, so how can we prove that this is indeed the transform domain equivalent for an inductor? We can do it in the same sort of way. We can come up with the ideal voltage current relationships for an inductor. That's a first order differential equation, and then we will unilateral transform it. What do we know about an ideal inductor? We know that its voltage, which we took here as being x of t, is equal to what? The inductance times the time derivative, so ddt, of the current I of t. That's just ideal inductor behavior. That's how we define an ideal inductor. I'm going to go ahead and take the unilateral transform of this whole thing and see what I get on that. If I go ahead and do that, I end up getting an x of s on the left-hand side, right? A transform of a variable is just the variables transform. And then on the right-hand side, because I have that inductance multiplying, and we know that a Laplace transform is a linear operator, we can pull that out front. And then we are talking what? The unilateral transform of a first-order derivative of a variable, in this case it. So I'm going to get an s times I of s. That s just means differentiate, right? That's the differentiation version of having that in the transform domain. S is just reflective of the differentiation operation in the time domain. And then I'm going to do what? I'm going to subtract off something based on the initial condition, which in this case is an I sub L at 0, something along those lines. Well, this one's already basically written in the way we want. I'm just going to multiply things out. What do I get? I get x of s as being equal to LS, that's the impedance of my inductor, times the current, right, I sub S. So voltage on the left-hand side, here's the voltage on the left-hand side, there's an impedance LS and a current, right? So this is the transform domain equivalent of Ohm's law. And then we knew there was another voltage in here as well, and that was minus L I sub L of 0. So just interpreting that guy as a voltage as well. Because of the minus sign out front, right, we know that the polarity on our circuit is going to go minus plus as I come out of that inductor, something along those lines. Okay, so what do? We have now two tools available for us, right? If I have a circuit that is drawn in the time domain as we normally do, I can transform that whole circuit, right? And I can replace things that are time domain expressions with things that are frequency or transform domain expressions. And then I can use my standard techniques like Kirchhoff's voltage law, Kirchhoff's current law, write all my loop equations, but just do it in terms of transform domain variables and solve it in the transform domain. Let's go ahead and demonstrate this through an example, but before I start that, I will note there are parallel forms, That's rather than the series forms that we showed, rather than the series form, just done, right, for both capacitors and inductors. And what I will say is read the book on that. Read the book. So the book will give it. It's very easy to prove these as well. It's a similar kind of thing. You just work with the direct first order differential equation that explains the ideal voltage current relationship of either the capacitor and the inductor, and you just rearrange it a slightly different way so that you can get a parallel form. So those are in the book. You can look at that as you like. Gives you another set of tools that you can do, because sometimes solving circuits using parallel incorporation of those initial conditions is easier than if you had it in a series. So let's demonstrate how this might be useful for us to look at a transform domain for a circuit, a time domain circuit. What I'm going to do here is I'm going to pick a circuit that is going to have an input x of t, okay, and I'm just going to let it be equal to 10 volts. And we're going to assume that voltage 10 volts has been going on for a really long time. So been out there for forever, basically. And then we're going to run that guy into an inductor. So I'm going to go ahead and draw an inductor in here. That inductor, I'm going to go ahead and let it have 1 Henry of inductance. And then I'm going to draw a node. And from that node, I'm going to have a resistor. And I'm going to let that be a 5 ohm resistor. And there's going to be a switch here. So I'm going to let that switch open, right, at t equaling 0. So at t equaling 0, the switch is going to open. And I'm going to go ahead and finish this guy, the first loop of this circuit anyway, coming down here. So before t equaling 0, right, we're going to have that loop closed. After t equaling 0, that loop is going to open. I'm going to let it continue and have another loop in here. I'm going to go through a resistor here, and I'm going to let this resistor be 2 ohms of resistance, something along those lines. And then I'm going to let this thing go through a capacitor, and that capacitor will tie down to that same thing. So I've got a pair of loops in here, one of which has a switch that is activated at time t equaling 0. The capacitance in this particular case, I'm going to let it be 1/5 of a farad of capacitance. So I've got a basic circuit here, an input that was 10 volts for all time. It's got an inductor, it's got a couple of resistors, and it's got a capacitor, and there's a couple of loops and then a switch that changes state in a particular time, which I've set to my time reference of t equaling 0. I need an output variable in this case, so I'm going to just let the current, right, going through that capacitor, or you could call it that second loop current, as being my output variable. So I'll call that guy y of t. Now, I could certainly solve this thing in the time domain, and it would involve something like the following. I would have to go ahead and write out the differential equations for the circuit. I'd have maybe a couple loop equations. I would have to combine those in such a way and get rid of, let's say, intermediate variables, whatever the case may be, so I get a single expression that relates output y of t to input x of t through a linear combination of output and input and their derivatives. Because I have a capacitor in here and an inductor, one of each, I know that there's 2 energy storage elements, so I would expect a second order differential equation. Because there's a switch going on in there, right, we know that before that switch opens, right, there's going to be some sort of steady state established in the circuit that's going to set up a current through the inductor, and it's going to set up a voltage across that capacitor. So you could think of those as initial conditions. And then once that switch opens at t equaling 0, right, we're going to see a different change in the circuit. And so we would normally think about solving this circuit's output voltage, not voltage, the current, through that capacitor, that y of t, right, for t greater than or equal to 0 once that switch opens. So this is gonna be written in the time domain, if you went through all the effort of doing it, is being written as a differential equation, a second order constant coefficient linear differential equation with two initial conditions, a current through that inductor, a voltage across that capacitor, as well as an input of 10 volts, right? And then trying to figure out what the output is. It would have both a zero input and a zero state response. For the zero input, I'd have to find the natural modes, I'd have to find the coefficients using those initial conditions. For the zero state, I'd have to find the impulse response of the circuit. Then once I had that impulse response, I'd have to convolve it with the input, and then I'd have to add those two pieces together. A lot of work involved in that. What I would like to do instead is I would like to try to see if I can solve this in a transform sense. Now I could, if I wanted to, I could sit there and draw out the differential equations, and then instead of solving it using time domain methods, I could just go ahead and transform those differential equations. That still requires me to come up with the differential equations. The advantage of me applying the transform domain analysis directly to this circuit is that I think I can avoid that step of finding the original differential equation. I do need to find the initial conditions though. So let's think a little bit about what happens in times t less than 0. In a time t less than 0, we're going to have that switch closed. And so I'm going to go ahead and just show that in here. I'm going to show that original state as being closed in there, something along those lines. And I've got a DC voltage source, 10 volts, right? That is going to be entering into this inductor that we've got in there. We know that that inductor, right, is basically a short for a DC signal, at least once it's hit that steady state. So we should get something like a 10 volts sitting out there at that node. I also know that the capacitor is like an open, so there should be no current flow going this way, right? No current flow going in that way, just because there should be that capacitor completely blocking it. That would also mean that this guy is 10, something along those lines. That actually tells me what the initial state is on that capacitor. I could say something like the voltage across that capacitor at 0 must be equal to 10, right? That's the only way that that capacitor is going to be blocking any current going through there. There has to be no voltage drop across that 2 ohm resistor. So I've got one of my two initial conditions in there. The other one comes out of what? If there was no current going through that 2 ohm resistor, that means all the current that might be coming from that 10 volt source, right, that's going through the inductor has to be shunting down through that 5 ohm resistor. And that 5 ohm resistor is a direct path to the ground part of this circuit. And we know that it's got 10 volts because that inductor, right, at least as far as DC is concerned in the steady state, is like a short circuit. So I'm going to have 10 volts going over 5 ohms. Well, that should mean that that current there, that I, should be equaling to 2. So I know that I sub L at 0, right, just before that switch opens, is going to be equal to 2, something along those lines. So I've done some really quick kind of calculations on this just to get an idea of what the steady state values, what would be the initial conditions of the circuit are. And now I think I have enough to solve it. Okay, so I'll summarize that just very quickly. With a little logic, so I'm going to just say with some logic, right, we see that there were two initial conditions supported here. We see that the voltage across the capacitor, right, just before the switch opens is equal to 10 volts. And we see that the current through the inductor just before that switch opens is equal to 2 amperes, something along those lines. And now I'm ready to go ahead and Laplace transform because I've got some initial conditions, right? If I go back to my originals up here, if I have an inductor, right, if I have an inductor sitting over here with some initial current, or if I have a capacitor with some known initial voltage, both of which I have here, I know how to write some equivalent circuits for those guys, and I'm just going to do that in this case. So coming back here, I'm going to transform this particular guy, and I'm going to be transforming it for times t greater than 0. Okay, so we are going to go ahead and let's transform. We're going to transform the circuit for basically t greater than equal, if you want, 0. We want to look at for the time after that switch opens, right, and get an idea of what its behavior is like. Okay, so for time t greater than or equal to 0, the input looks like a 10-volt unit step. Any of the 10-volt before that, its only impact, its only effect on the circuit was establishing those initial conditions. So the initial conditions capture everything associated with that x of t equaling 10 volts prior to t equaling 0. So for t greater than or equal to 0, I'm going to be looking at x of t being 10 u of t. This is also described in the book, so if you're having a little difficulty getting your head around that idea, just read it in the book and it will give you another perspective on that. So I have something like a x of t equaling 10 u of t. Now if I Laplace transform that guy, right, if I Laplace transform that guy, I should get a 10 over s, something along those lines. So I'm going to start out this circuit, right, with the voltage because I had an input. That input for t greater than or equal to 0 is like a 10 u of t, and the transform of 10 u of t is just 10 over s. So I can write that guy as a 10 over s on that voltage. I know that that is going to go into an inductor, right? So there's that inductor. And that inductor has an impedance, right? That impedance of that inductor is L times S. If I go back there, it was a 1 Henry inductance. So the inductance here is going to lead to an impedance of just S, right? 1 times S. So that's my inductor's impedance. Because there was an initial condition, I know I can put that initial condition generator, and I know it goes something like a minus plus. That was something we just had derived, and that minus plus in this particular case is going to reflect the initial current through the inductor, right? And that was just IL of 0. So this is going to be 2 in there, something along those lines. Now, I would normally think about having that joint, that node sitting here where current, right, could split. It could go this way or it could go this way. It could go down one of those two paths. But the second that switch opens, right, at t equaling 0, now I just have a resistor, 5 ohms, dangling, and there's no way current can go there because it's open, right? That 5 ohm resistor is now no longer relevant to this circuit. It is completely, it can't store energy, right? It's a resistor. Resistors don't store energy. It's been completely disconnected from the circuit because of that switch opening. So I can just ignore that guy. I won't even draw it because it no longer comes into play. And it's part of the reason that this circuit has sort of an interesting dynamic, right? When that switch opens, the topology of the circuit actually changes. It went from something that had a inductor, a capacitor, and 2 resistors, basically to something that has an inductor, a capacitor, and 1 resistor. So when I hit that t equaling 0 and the switch opens, right, this guy here was completely disconnected and I don't have to worry about it anymore. What came in next? Well, I knew in there was that 2 ohm resistor. The impedance of a resistor doesn't depend on frequency. It's just going to be the resistance, which in this case was 2 ohms. And then I do what? I'm going to turn the bend and go into a capacitor. The impedance for a capacitor is 1 over CS. The C here is 1/5. So 1 over a 5th S would end up giving me a 5 over S as the impedance of that device, of that capacitor. And then what do? I need another initial condition generator because there was an initial voltage on that capacitor. Now the polarity is a plus minus, right? And we knew that the initial voltage on that capacitor was 10, and that initial condition generator needs that initial capacitor voltage divided by S. So I'm going to have a 10 over S. And then I can just sit there and finish out the loop. So I can come in here and close this guy out. And I know that I still have the voltage going through, not the voltage, the current going through that capacitor as being my output variable, y of s. Okay, so what have I done? I've basically taken my original circuit, which was written in a time domain type of a representation. I used the knowledge of that switch that was in there to help me establish what the 2 initial conditions of the circuit were being. And then I went ahead and took the unilateral transform of that circuit for time t greater than or equal to 0. That gave me a transform domain version of that circuit, which has a really neat kind of advantage, right? Those 2 initial conditions now are explicitly incorporated into the circuit diagram, right? Those initial conditions show up as physical elements, if you will, and so they're much more directly used. It's much more difficult to somehow miss them or misuse them in this transform domain equivalent. So now I've got a circuit and I just need to solve it. How do I solve this guy? Well, I've got a single loop, and I could certainly apply in this particular case this idea of summing up the voltages around a loop has to be equal to 0. So I'm gonna come over here and I'm gonna sum, right, the voltages over the loop, or around the loop, maybe it would be a better way. The voltages around the loop, right, around the loop. have to be equal to zero. They have to sum up to zero. This is Kirchhoff's voltage law, right? And we're just doing it in a transform domain circuit. So what are the voltages here? If I take a look at this, I'm going to have 10 over S, right? 10 over S. And then I also see in there that there is another source too, and it has the same polarity, so I can add that. These are all voltage sources in that loop. And then I see one more voltage source, but it's got an opposite polarity, so I'm going to have a minus sign in there, and that's going to be minus 10 over S, right? So the first 10 over S was from the original input. The second one was from the initial current going through the inductor, and then the third was because of the initial voltage on the capacitor. Those are all the voltages in this loop. The sum of all those voltages, right, have to be equal to the current times the impedance. This is Ohm's law, right? V equals IZ, basically. And so what is my current here? Every single element shares the same current, so it's just going to be Y of S, right? I get Y of S. And then that Y of S needs to be multiplied by the various impedances. The first one is going to be S, right? And then 2, and then 5 by S, right? We just add those impedances together for these guys in series, all shared by the same current. Okay, now I have a very simple equation, right? All I see in this one is the variable of interest, although it's in the transform domain. I see Y of S, which I should be able to solve for. I'm going to go ahead and try to do that. And the first thing I'm going to notice is that 10 over S and that minus 10 over S are going to cancel, so I don't have to worry too much about that. And I'm just going to have 2 on one side equaling Y of S times some polynomial P. So let's go ahead and solve for Y of S in this case. I get Y of S, right, being equal to, and I'm going to have 2 over S plus 2 plus 5 over S. Now this isn't in exactly the most convenient form because I have a denominator that has some positive powers of S and then like some negative powers of S, that 5 over S. So if I multiply top and bottom by S, I haven't changed anything, right? That's just a fancy one. And it's going to get it in the more standard rational function form. It'll just make it easier for me to kind of figure out what's going on with this guy. So let's go ahead and take this Y of S then, and it should be equal to a 2 times S by, I'm going to have an S squared, right, plus 2S plus 5, something like that. This is a transform domain for my output current, right? That Y of t. And if I want to get Y of t, I just have to be able to invert transform this guy. So I have to be able to take the inverse transform of this guy. I need to, right? I need to inverse transform this. I need, right, the inverse unilateral Laplace transform to get this quantity that I wanted to know, right? The output current, Y of t, something along those lines. Well, if I take a look at the denominator here, it is second order. And by the way, that should make you happy, right? A second order kind of denominator here is consistent with this idea of a second order circuit. And so I've got this second order denominator down there. There's going to be two roots in there for sure. And in this particular case, what I would like to do is I'd like to think about what the roots are. If I root it, I find out that they are complex. They are complex roots, okay? Now, I could find those complex roots. I could find a lambda 1 and a lambda 2. I could factor it out, and then I could use something like a method of clearing fractions or using Heaviside cover-up method, and I could break it out into 2 terms, invert each one of those terms, and get a time domain expression. But it would look like it had some complex components on it. What I would like to do is I'd like to demonstrate a slightly different method. Sometimes when we have complex roots, people don't want to deal with those complex factors and the complex coefficients that go along with them, because in the end, you have to simplify those guys. We know a circuit doesn't output a complex current, right? It outputs a real current. So you would have some simplification to go there. And so if you're just willing to do a little bit of additional study on partial fraction expansions or working with these guys, you can use quadratic terms. You can use things that are quadratic in form and avoid having to root out or work with the complex roots individually. You'll work with the complex conjugate pair of roots together, which when multiplied out all gives you just real coefficients. Now, there's a lot of different ways to do this. I'll let you read in the book the general things here. What I'm going to do is I'm going to manipulate this expression for Y of S so that it matches things in our Laplace transform tables of common Laplace transform pairs. And what you'll see in those tables of Laplace transform pairs, the formula sheet from Blackboard is got these in a nice list. You're going to see some first order ones, and you're going to certainly see some second order ones. And we're going to work on those second order ones. And what I'm going to note here is that there is this s squared plus 2s term, and I'm going to use a method called completing the square. Completing the square will help me get a form that is going to match these tables. So let's go ahead and work on that. I'm going to have my y of s, no problem there, is equal to, right, and I'm going to go ahead and draw this out, and I'm just looking at that s squared plus 2s, and I'd like to make a perfect square that gives me this term s squared plus 2s then plus whatever is left over of that perfect square. So I need an s plus something squared, right, whose squaring then will give me an s squared plus 2s. Well, we can see the s squared for sure, right? If you take s plus something and multiply by s plus something, you are going to get an s squared. Let's go ahead and put in the something here as 1, because I think I can do this by inspection. And s plus 1 squared, right? If I wanted to go through on a little side issue, I can go s plus 1 squared, right? That's an s plus 1 and an s plus 1. And if I do that, that's an s squared plus 2s plus 1, right? So that's a perfect square. I've done this because the table entries that I'm going to use to invert transform this there's table entries that have things in this form. For a quadratic factor in the denominator, they have some that have this perfect square form in the bottom. So if I replace or think about that s squared plus 2s and I write it as an s plus 1 quantity squared, I've taken care of s squared plus 2s plus 1. So I've taken this s squared, I've taken care of this 2s, and I've included 1 of the 5 there. What does that leave in balance? That leaves in balance 4. So this is just a different way of representing that denominator. I've represented it as a perfect square plus a constant. And the reason I did this, pure and simple, was so that I could match something in the table, and so I could avoid dealing with complex conjugate roots, which would have required a little bit of additional simplification. Now, if you take a look at the table entries that have things like an s plus something squared plus another thing squared, in this case, that 4 is just also a square, it's 2 squared. If you find the entries that have that, we know that our numerator, right, our numerator up here has an s in it. The only table entry that has an s in the numerator has to have it as part of that perfect square guy. So I'm going to need an s plus 1 in the numerator. So I'm going to go ahead and just put in what I know I have to have. I know I have to have an s plus 1, even though I don't see it in my original run, right? I don't see there's no 1 in there, right? No 1 in there. So I'm going to have to find a way to deal with that. I'm going to take care of the s term first, and then there was 2 times that. So I'm going to go ahead and multiply by 2 here. So I have a 2 times s plus 1. That gives me the 2s, right? So if I come back here and I think about the original, right? I ended up doing with, as it is written right now, right? I see that I get the 2s, check. But then there is this 2 times 1. So I had a plus 2 that was like extra, right? So I'm somehow, so I can match this table entry, I'm getting something with an extra term in there. Well, I don't want the extra term in there, really, because that changes the answer. So the way I could get rid of that extra term is I could just separate it or subtract it out. So if I add to this a minus 2 overall, that same stuff in the denominator, and s plus 1 squared plus 4, this whole thing, right, this whole piece here now is fully equivalent to this guy. The denominator, an s plus 1 quantity squared plus 4, you can certainly multiply that out, and you see you get an s squared plus 2s plus 5. The numerators there you could add together. So I'd get a 2s plus 2 minus 2. That's just going to leave me a 2s. So certainly that's equivalent to this guy up there. Why did I go through all of this? I went through this because if you take a look in the tables, right, this is available table entry, right? That's in the table. So that's an available table entries, and so is that one. So I've got 2 guys now written. I've just broken this guy up in a different way. Partial fraction expansions are one way to break it up into really simple terms. Here I'm doing a little bit different path. I'm breaking it up into different terms so that I can avoid looking at the complex conjugate roots. And I could have done it that way. I just wanted to show a different method here. So I ended up working with the quadratic factors that are available in this table so that I can easily invert. Okay, so now I've got it in a form. I did this completing the square and found a form that utilizes stuff that are purely within the table entries. So now I go ahead and do what? The inverse unilateral transform And this is by tables. I'll let you go ahead and cross-reference with the tables that are available on Blackboard for the class. And what you'll see in this case is that on the left-hand side, I had y of s, invert transform that guy, I get y of t. That first term, 2 times the quantity s plus 1 over an s plus 1 squared plus 4 ends up giving me 2 times, and I'm going to get an e to the minus, because of the 1 here, right? The 1 here, that's what controls the amount of this first term out front. It's going to be 1 times t, so I'm going to get 2 times e to the minus t, and then I'm going to have a cosine of, and I'm going to take the square root, basically, of this piece over here. So 4 square rooted is going to be 2, so I'm going to end up getting a cosine of 2t. This becomes obvious if you just take a look at the entry. It has something like this. They have something like an s plus a over an s plus a squared plus b squared, right? This thing has a transform of an e to the minus a t cosine bt is something is what I'm using here. That's the table entry. There's a similar table entry for the second term, and if you go ahead and take a look at that, I'm going to get a minus 2. There's just that. Oops, actually I got that one wrong because there's a b in that one. So let me go ahead and write it out. There will be a minus sign in there, so I'm going to get a minus sign. The second table entry that I have in there looks something like this. It has not an s. It has a form of something like b over s plus a quantity squared plus b squared. That guy has an e to the minus at sine now bt, something like that. Okay, so in this particular case, my b is 2, and it's already got that b in the numerator, so I'm going to just get in here in e to the minus, I've got something going on here. I'm going to try to erase that and see if we can get this cleaned up a little bit. That's an e to the minus t now, cosine of t. Let me clean this all up. And oh, because it was unilateral stuff, we should have gotten a u of t on all of this. So let me clean up just a bit more. Y of t then is equal to, and I could write this out as an e to the minus t, right? And then I could have 2 cosine 2t minus cosine, not cosine, boy, did I ever get that one wrong. I don't know where that came from. That was sine. I needed my sine term, right, 2t. So I end up getting that sine piece in there. So I'm going to get a minus sine of 2t, and then it was u of t. And that is my final answer in this case. All right, so let's just summarize what we did here. I'm going to run back through this a little bit just to kind of highlight what we talked about. I had a circuit here which, if I wanted to go through the effort of finding the differential equation, I could relate input x to output y through a second order differential equation. I could solve that using time domain methods, so I could find things like the zero input response, and I could find the zero state response after I had found the unit impulse response and done some convolution, and I could have added those two guys together and got a total response. I also could have taken that differential equation and applied a unilateral Laplace transform to it and solved it in the transform domain. Instead, I ended up just transforming the circuit. That helps me avoid the step of needing to find the differential equation. It allows me to incorporate those initial conditions in a very explicit and easy way, and I can solve it all in one step without any kind of calculus, without any finding of unit impulse response, without any of those kind of hard things. I just end up doing something algebraically. I did a little bit of pre-work up front to find out what the initial conditions were, which was generated because of that switch inside this circuit, and then unilateral transform that guy, and I got a simplified expression, right, a simplified circuit that explicitly incorporated things like initial conditions. I still analyze that with my normal kind of circuit analysis. In this particular case, I added up all the voltages going around this loop, and I know that's equal to the current times all the impedances. It's basically the transform domain version of Ohm's law. And so doing that, I ended up getting an expression that was purely in terms of y. I found out y was a rational function. Now, it had 2 roots. Those 2 roots were complex. I didn't actually do it. You could do that if you wanted. You could demonstrate that there are complex roots here. So there are complex roots in this particular case. I could have just done my standard, break it up into 2 simple first order terms, which would have had complex modes, and it would have had complex coefficients. And when I invert transform them, I would have had some additional simplification step to get what I know has to be the current here, an expression that looks real. Instead of doing that, I avoided that simplification step by just recognizing that if I keep a complex root combined with its conjugate, okay, that there are usually table forms that allow us to handle these conjugate pairs using all real coefficients. I scanned through those tables and I noticed that there is 2 table entries that look something like, right, this s plus a over s plus a squared plus b squared, and something that looked like a b over s plus a squared plus b squared. And the game here was really just take my original expression, right, and write it in terms of those 2 guys. Now, there are other table entries that allow you to do it in a different way. This one, to me, was just the simplest way. So I did a little bit of manipulation in order to get these expressions that would carry for these 2, and then it's just a matter of inverting by tables, in which case you can write down the answer, right? You can write it down without any kind of real difficult mathematics. And so we ended up getting the overall response on this particular circuit, right, as being something that oscillates at 2 rads per second. That's the cosine 2t and the sine 2t, right? And it also has a decaying envelope in it, right? So there's an e to the minus t type term on this thing as well. Okay, so I think that concludes that example. There's one more thing I'd like to do before I end out the lecture, and so I'd like to look at some block diagrams. We're getting really close to talking about how to realize systems, and we're going to adopt a transform domain viewpoint of system realization, and we'll start that with some real basic block diagrams. We've looked at some of these block diagrams before using time domain expressions. I'm going to work with transform domain expressions, and we'll look at one we did not look at it in the time domain, just because it was so incredibly, it would be so incredibly difficult to analyze it with a time domain expression. So let's consider some basic block diagrams. So let's look at right what I'm going to call block diagrams for systems, right? And these are going to be in the Laplace domain. Okay, so we're going to just take a look at some representations of systems using block diagrams in the transform domain. The first one that I'm going to take a look at is just the basic block diagram that we started the class with, that I can have an input x of t, right? And it can go through a system that, if it was a linear time invariant continuous system, we know that we can represent all the input-output behavior of that system through an impulse response, h of t, to generate out some y of t, right? That's a block diagram in the time domain. If I transform that guy, right? If I do my Laplace transform on this guy, I can get another one over here, right? That is still that simple block. It's just now instead of x of t, I'm going to get x of s. And instead of y of t, I'm going to get y of s. And we know that the transform of the unit impulse response, h of t, is just the system function or the transfer function, h of s. So a transform domain equivalent for the basic time domain block diagram, input-output block diagram for signals and systems interaction, right, is identical in appearance, right? We just change our time domain expressions to our transform domain expressions. Now, there's some basic configurations, right? We know that there are some basic configurations in how we hook up blocks, right? And we looked at a lot of these guys back in the time domain. So we did stuff like this. I took a look at, for example, a signal x, right? And let's just go ahead and do it in the transform domain now. I'm going to stay totally in the transform domain. So I can look at this particular guy as having my x of s, and it's going to go ahead and feed into a system. And I'm going to let this first system have a transfer function, h1 of s, for example. And then I'm going to let the output of that go into another system, right, which I'm going to call h2 of s. And then I'm going to get my overall output. So I'm looking at, in this particular case, a series connection of 2 systems. And I'd like to think about them in the transform domain. And what is the single block equivalent of these guys? Well, we know it still has an x, right? It still has an input x, and it should still, if it's equivalent, have the output y of s. I just need to find out what the transform domain single block representation has for a system function or a transfer function. If this was in the time domain and we had systems in cascade, in series, right, we know that the overall impulse response would be the convolution of each individual impulse response of whatever systems were in cascade. So the overall impulse response would be h1 convolved with h2. But if I transform that guy, right, H1 convolved with H2 transform becomes multiplication. And now our transfer function is easy. H1 of S times H2 of S. Got that a little bit crowded, but it's just multiplied. Let's go ahead and clean that up just a little bit. I'll make this whole thing a little bigger just so we can make sure that it's readable. So make the box a little bit bigger here. I'm going to go ahead and still have my output Y of S. It's just now the transfer function is H1 of S times H2 of S. No convolution is required. So systems in series, right? You just multiply their transfer functions. Very, very simple. If I talk about a system input, right, feeding into not a series, but a parallel configuration of systems. So I'm going to go ahead here and think about a system H1 of S being one of the path inputs for my input, and H2 of S also being a path input for X, right? And then I'm going to take the output of those guys, sum them up together to give me my overall output Y of S, something like that. Well, we had also seen this in a time domain expression, and we knew that there was a single block representation for this system as well, right? And because it was an equivalent one, we still have our input X of S, we still have our output Y of S, and we just needed to find out what was the equivalent single system. For systems in parallel, their impulse responses add. Laplace transform is a linear operator, so addition stays as addition. And so the transfer functions here are going to be just an addition, H1 of S plus H2 of S, something along those lines. So if you have systems in parallel, right, the overall transfer function is just a sum of the individual transfer functions. If you have systems in series, the first thing we did, the overall transfer function is a product of the individual transfer functions. Okay. So let's do something that's a lot more difficult, and it would be one that I think would be exceedingly challenging to look at in a time domain kind of analysis. So we're going to look at a system that has an input X of S. I'm going to go ahead and jump directly into the transform domain, and it's going to go first into a summing node, and I'm going to let that path be added into that summing node. That is going to go through a system whose impulse response, I'm just following the convention in the book, is going to be indicated by something I'm going to call G of S. And there will be an output of this system, Y of S. The kicker here, the quirk, is that I'm going to take that Y of S and I'm going to feed it back through another system. Okay, so I'm going to come back and feed through another system, which I'm going to call H of S. And that guy is going to get subtracted from the input. So this is sort of an interesting configuration. This is found all the time in control systems. So for those of you who end up going on and taking one of the many controls classes we have available in the department, you'll absolutely see this. This is a basic configuration for a control system. You have some system of interest, I'll call that G of S, and we would like to change part of its characteristics. We would like it to have better behavior. We'd like to modify its behavior, and we can do that through the application of a negative feedback control system, that H. And we would like to know what is the overall transfer function of this system. If you looked at this in the time domain, because of that feedback, that G of S represents a differential equation, could be a 100th order differential equation, right? H of S could be a 100th order differential equation, and now you've got this messy feedback path of 100th order differential equation with another 100th order differential equation. It becomes almost impossible to take a look at this guy using time domain analysis. Transform domain, though, is going to be pretty easy. I'm going to set up a variable of convenience. I'm going to call that something like epsilon, just the output of that summing node. This would be a common kind of strategy. I'm going to write an equation for that because this equation is going to help me in my pursuit of finding the overall transfer function of the system. So what do I know? I know that epsilon, or that E, if you want to call it that, is equal to X, right? That's the path coming in, and it's going to be minus whatever comes out of that H system. Well, what comes out of the H system? It has an input, which is Y, right, going through that system. That's just multiplied in the transform domain. So no convolution, it's just multiplication. Input times the transfer function. So I'm going to get something like Y times H. And I'm leaving off the S's right now. We can add them back in later as we need to. So E, right, equals X minus Y times H. If you did this in the time domain, you'd have E equaling X minus Y convolved with the impulse response, H of T, something like that. That would be a lot more complicated. What is Y? I can also write an expression for Y, because Y is just the output of that system G with E as an input, right? So I know that y is equal to, and if it was time domain, I would have the E signal convolved with the impulse response little g of t, but in the transform domain, it's just going to be multiplication. So I'm going to get E times g, something like that. All right, so now I have two equations. They have some x's in there, the input. They have some y's in there, the output. But then they've got this kind of intermediate variable of convenience, e. And what I really want is I want an expression that just has x's and y's. So I would like to go ahead and take this first expression for e, right, and plug it into there so that I can get rid of the e's and just have something that has x's, y's, and the systems under consideration. So if I go ahead and do that, what do I end up getting? I'm going to get y, right, equals, and I'm going to have x minus yh, right, times g, something along those lines. Go ahead and multiply out those terms on the right-hand side. I'm going to get xg, right, minus ygh. I'm going to rearrange this so I can get all the y's on one side. So I'm going to have a y plus ygh equals xg, and then I'm going to pull y out by itself. So y times 1 plus gh, right, equals xg. What do I know about a equivalent single block system, right? There's going to be some overall h equivalent, right, with an input x and an output y. And what's the relationship with a single block? We saw this at the start, right? Y equals whatever the transfer function is, we're going to call that h equivalent, times x. And I can find out if I just divide both sides here by x, I find that h equivalent, right, is equal to y over x. That's something we saw in our last lecture as well. You can find the transfer function, right, for a system by taking a ratio of its output to its input. So coming back to this expression that I've been working with, I've got some y's and some stuff and an x and a stuff. If I bring the x over to the other side, so divide both sides by x, and then I bring the 1 plus gh to the other side, so divide everything by a 1 plus gh. What I can get on this is I can get y by x, which I know is that h equivalent, right? And that is going to be equal to, in this case, g over 1 plus gh. Okay, let's get the s's back in there. The h equivalent, the equivalent transfer function as a function of s, was a ratio of the output to the input, which we see in terms of the existing functions in that block diagram as being g of s over 1 plus g of s h of s. Now, for typical systems, both g and h are rational functions. A product of rational functions, g times h, will still be a rational function. Add 1 to it, it's still a rational function. Take a quotient of a rational function over another rational function, it's still a rational function. This thing is going to remain a rational function if the original ones were a rational function, but it's going to be a messy expression. Easy to do in the transform domain, incredibly hard to do in the transform domain. I can take this now and come up with my equivalent kind of representation. So we had what? We had x of s, right, feeding into this summing node. The top part was getting added. We knew there was a bottom path that was getting subtracted. That went through this first system, right, which we called g of s, the output of which was the overall system output. But this thing utilized a feedback path through another system, oftentimes considered the control system, and that was some h of s, and we subtracted that from the input. And what we can do now with this whole thing is we can say that this whole thing is equivalent to what? It's equivalent to a single block system for which we have an input x of s, right? We have an output y of s, and the system's transfer function, HEQ, right, is equal to, we just had that up here, g of s, right, over 1 plus g of s times h of s. This is the classic feedback configuration for a feedback control system. I think that's enough for this lecture today. Next time we're going to talk system realizations. It's a really enjoyable, kind of easy lecture. If you've been a little overwhelmed with some of the math, this next one is just a lot more graphical in nature. It doesn't have any kind of heavy-duty math. It's very, very straightforward and easy. And so hopefully that next lecture will be kind of a nice break from some of the heavy math.